the notion of inversion number was introduced by the mathematician Kramer in about 1750, and the context was very interesting. He was describing an algorithm to solve systems of linear equations, and that algorithm is now called Kramer's rule, and for that he needed to define the determinant, and Kramer defined the determinant of a matrix. Let us say it is x I j, an n by n matrix. He defined it to be the sum over all permutations. Let us say sigma is a1, a2, an, then it is just minus 1 raised to the number of inversions of sigma x 1 a1, x 2 a2, x n a n. Okay, so here is a question. Is there a permutation with no inversions? And I am sure most of you have guessed that there is at least one, right. You just take sigma to be 1 to up to n written in increasing order. This has no inversions, because everything that is smaller appears to the left of everything that is larger. Is there anything else? Well, for this we can use the inversion table if you wish. If it has no inversions, then its inversion table must be all zeros, because the inversion number is the sum of the entries in the inversion table. And so, remember, inversions of sigma equals B1 plus B2. Every inversion is counted by one of the BJs. So, if sigma has no inversions, then its inversion table should be 0. So, when you run that algorithm, you will construct sigma equals 1, 2. So, this is the only permutation with no inversions. Okay, that was easy. Let us make it slightly harder. What about permutations with exactly one inversion? Well, you may have guessed the answer, but let us just look at the inversion table once again, right. So, inversion table, well, it must sum to 1, right. So, it has to be of the form, you have a bunch of zeros, then you have a 1 somewhere, and then again you have a bunch of zeros, and the last thing has to be 0 because of the condition that B n lies between 0 and 0. The last thing has to be 0. So, there are n minus 1 possible positions where you can put a 1. There are n minus 1 possible positions where you can put your 1, and so the number of permutations with exactly one inversion is n minus 1. What are these permutations? So, I will show you, it is quite clear once I write them down. So, we have this permutation 1, 2, 3, 4 up to n, this has no inversions. you just take 1 and 2 and switch them around, 2, 1, 3, 4. I will call this S1. So, this is a permutation where I switched 1 and 2. Similarly, so you can see clearly that this has no inversions except 1 comma 2. Similarly, if I take 2 and 3 and switch them around. So, here I have switched 1 and 2, here I have switched 2 and 3, and I am leaving everything else exactly as it was in the identity permutation. And S3, 1, 2, and then I switch around 4 and 3. Keep everything else the same. In general, I would take Si to be the permutation where I switch I plus 1 and I, and everything else is kept in order. And what can I be? So, I has to be between not 0, I has to be between 1 and n minus 1, and this gives me the n minus 1 permutations which have exactly one inversion. These are sometimes called simple transpositions. Okay, one more question about inversions. So, which permutation has the largest number of inversions? Again, I am sure you will be able to guess the answer quite easily, but again let me go with the inversion table which I seem to like so much. So, what is the inversion table going to be? We need to max out all the B's, right. So, we need to have the inversion table where every Bi is the maximal possible. So, B1, remember it lies between 0 and n minus 1. So, the inversion table has to be B1 needs to be n minus 1, B2 needs to be n minus 2, and it goes all the way down to 0. And when you run the algorithm for reconstructing the permutation for this, you will see that you will put n first, then you will put n minus 1 to its right, then you will put n minus 2 further to its right, and so on all the way down. You will add each smaller number to the right of the previous numbers, and the permutation you get is the one where the elements of 1 to n are arranged in decreasing order, sort of the other extreme of the identity permutation where they are all arranged in increasing order. Here is a simple sorting situation. I have these 4 pencils of different lengths and I want to sort them so that going from left to right they are in increasing order of length. Now, it is difficult to compare 2 pencils that are far apart. For example, this pencil on the left and this pencil on the right, I am not sure which is larger. Maybe if you have better eyes you can tell, but unless they are next to each other it is not so clear which one is larger. So, I have this situation where I have an unsorted set of objects and I can only compare things that are adjacent to each other, and so how do I sort them into increasing order? So, what you do is, okay, so you go through this list of these pencils from left to right and look for the first pair that are out of order. So, this second pencil and third pencil are out of order. The third pencil is shorter than the second pencil, but it is to its right. So, let me move that to the left. And now I have corrected one of the anomalies, but I have created a new one. Now, the second pencil is shorter than the first pencil. So, let me interchange these two. Okay, so the first 3 look okay, but this fourth pencil is certainly shorter than the third pencil, and so I interchange these two. And now they are all sorted. So, you see that just by interchanging adjacent pencils that were out of order, I have been able to rearrange all the pencils in increasing order of length. Okay, so I told you that permutations come up in the study of sorting algorithms. So let me explain the notion of sorting an algorithm with simple transpositions. So now I will think of a simple transposition as an operation on a permutation. So I will call it again SI. It's related to the permutation, which is a simple transposition, but let me not get too much into that. So if I have a permutation sigma A1, A2, AN, I will say SI sigma. This is a new permutation where I take A1, A2, but I interchange AI and AI plus 1. Okay, so you can think of this as an operation from permutations to permutations, and you can do this for any I between 1 and n minus 1. Now, we have seen while trying to sort our pencils in increasing order of height that we could always achieve this by just switching two pencils that were next to each other, which were easy to compare in size. So, the fact is you can take any permutation and change it to the permutation where everything is in increasing order, the identity permutation, by a sequence of such simple transpositions. Okay, before I explain that process in more detail, let me just clarify certain points. So, in a simple transposition you are only changing two things that are next to each other. You might have inversions involving AI and AJ that are far from each other. I could be much less than J. So, but here we are only allowing you to swap things that are next to each other. So, it is not clear a priori that by just swapping things that are next to each other you will be able to sort your permutation, right. So, these simple transpositions they occur whenever we have what is called a descent. So, let me define a descent. I is called a descent of sigma in perm n. Let us say sigma is A1, A2, An if AI is greater than AI plus 1. So, this AI and AI plus 1 are in descending order at the position I. And here is a simple observation which I will state as maybe let us call it a lemma. The following are equivalent. The first is that sigma is the identity permutation. The second is that the identity permutation has no inversions, and the third is that sigma has no descents. So, what it is saying is that if there is an inversion, there has to be a descent. Okay. So, if two things are out of order, there have to be two things consecutive that are out of order. And let us prove this. Well, I think we have already proved that 1 is equivalent to 2 using inversion tables. But anyway, 1 implies 2 is completely obvious, and that 2 implies 3 is also completely obvious, because a descent is a particular instance of an inversion, right. So, we just need to show that if a permutation has no descents, then it must be the identity permutation. Well, if a permutation has no descents, so we just need to prove that 3 implies 1. So, if sigma has no descents, then what does that mean? Well, that means that A1 is less than A2 because there is no descent at 1, A2 is less than A3 because there is no descent at 2, and so on. And so, they are really in increasing order. A1 has to be 1 because the least of all the numbers, A2 has to be 2 because it is the least of all the numbers after removing 1, and so on. And so, what we get is AI is equal to I for each I, and so sigma is the identity. Now, we are ready to state the main theorem about sorting using transpositions. Theorem: if a permutation, let us say sigma in perm n has k inversions, then it can be sorted and when I say sorted, I mean changed to the identity permutation. With exactly k simple transpositions. Let me illustrate this theorem using an example. So, we had this permutation with 3 1 4 2, and this had 3 inversions as we had seen. So, let us just write down a table where we will slowly sort this using inversions. So, at each stage we will have a permutation sigma, we will also keep track of its inversion table. And at each stage I will apply a certain simple transposition SI. So, let us maintain this table. So, we start with 3 1 4 2 and let me just look for a descent. Okay, at each stage I will look for the first descent. So, 3 1 is a descent. Oh, let me write down the inversion table. So, the inversion table here, 1 has there is one thing to the left, 2 has 2, 3 has 0, 4 has 0. Okay. So, 3 1, well that's a descent, and so let us correct that. So, I will apply S1, I will interchange 1 and 3, and so what I get is 1 3 4 2, and what happened to my inversion table, what we get is 0 right, yeah, 0 2 0 0, and then let us look for a descent. Now, there is no descent at the first position, there is no descent at the second position, there is a descent going from the third, between the third and fourth entries. So, 4 2. So, we need to apply S3 here, and what we get is 1 3 2 4, and what happened to the inversion table? Well, we have reduced one of the inversions again, the inversions involving 2 has reduced, this has become 1 0 0, and now let us look for an inversion. Well, so we have this no, let us look for a descent. So, we have 1 3 2 4. So, 3 and 2, there is a descent there at I equals 2. So, we apply S2 again, and what we get is 1 2 3 4, and this has inversion table 0 0 0 0. And so, we have sorted this using exactly 3 simple transpositions corresponding to the 3 inversions, and what you see from the inversion table is that each simple transposition which corrects a descent. So, we are applying simple transpositions exactly when we see a descent. You do not necessarily have to apply it to the first descent that you see going from left to right, you can apply it to any of the descents. Each time you do that, you will be reducing exactly one of the entries of the inversion table, and this process cannot continue indefinitely. At some point, namely after exactly k steps, where k is the number of inversions of sigma, you would have reduced the inversion table to 0 0 0 0, which means that you would have obtained the identity permutation 1 2 3 4. Okay. I am not going to bore you by going into all the details of the proof, but I would encourage you to try to fill in all the details yourself and try to write it down.